what do we mean when we say that we want to maximize object detection quality, and what does the no cost aspect of it mean? Now, theoretically, the costs could be anything. It could be costs of gathering data, training models, there's a time cost, and so on. What this talk aims to do is provide some ways of estimating lower bounds on the quality of object detection. We'll get into a lot more detail, and I'll show you some very specific examples with some results which could act as benchmarks. You could probably try and reproduce the same method on a certain object detection task and try to get your own lower bounds for a particular data set. That's broadly the idea. So by the end, you will have a different perspective on object detection. Typically, when we deal with object detection, the tendency is that you either have enough compute or you have enough data, or both, and eventually the model will run, right? But what I'm going to do is convince you to turn your focus towards the data itself, not towards the model. Data augmentation, deeper models, and better compute, all of those things come after you already have the data. So what is the maximum inference that you can extract out of the data itself? That sort of acts as your lower bound, independent of the model, right? So yeah, we are going to learn ways of establishing lower bounds on the performance of object detection models, independent of the model architecture. Whatever you do with the model is only going to push it higher, right? So let's get started. Let's start with a simple overview of the types of computer vision problems. I'm sure everybody knows this, but I'm building up to something here, right? The simplest is binary classification. You have an image and you need to, it either belongs to one class or the other. And these classes are what we call mutually exclusive and collectively exhaustive, which means that exactly one class out of two can be present in a given image, right? So, and what you predict out of this is simply a probability distribution, which is like tossing a coin. It's exactly like tossing a coin. The coin may be biased, of course, right? The second, when you make the same problem a little more complex, it's object detection. Now you are concerned with not only what is in the image, but where it is in the image. So there is a regression component to this, right? There is a positioning component to this, as well as classification, of course. And by this time, your binary is not just multi-class, it's multi-label, which means that any number of labels could be available, none of them could be available, and any labels could be available more than once in a particular draw. And then maybe the most complex task that I can think of is what we call semantic segmentation, where every pixel is labeled independently. So this also is a multi-class problem, except that your sample is one pixel at a time. And then depending on how you can group those pixels together, you can count objects and so on. So what we see here is that the task becomes more and more complex. And as it becomes complex, the training data starts acquiring additional attributes. Now, by training data acquiring attributes, we don't mean that the images themselves are acquiring attributes, or training labels are acquiring attributes. You see, P2, where P1 and P2 sum to 1. And the same thing can be generalized to K classes, right? But then there is a regression problem, and then there is an aggregation of binary classification or multi-class classification for every single pixel. So that's our labels acquiring extra attributes. Earlier, it could just be an array of zeros and ones, but here it starts with an array of zeros and ones, then it goes to being a one-hot encoded matrix, then it goes to being a really complex structure where you have labels and you have bounding boxes and things like that. So your Y, if you're fitting on X and your target is Y, your Y becomes more and more complex. So let's try and see a very simple example of this. Like, how would you try and train a machine to play board games? So a couple of friends and I were playing Monopoly, and I realized that I lost one die. Right? And for some reason, it did not occur to me that I could just simulate a die toss using a computer, because I don't know what I was thinking at that time. So we thought that, okay, let's take a coin and try and see if we can toss that coin to somehow simulate the die toss, right? So you could toss a coin 3 times to get 8 possible outputs, and if you could do that, then in that case 6 of them could be bent into the 6 faces of the die, but that wouldn't be a uniform distribution and so on. So that sort of led me to thinking what you could do with these different attributes that the targets acquire, especially in a computer vision problem. So let's take a look. How would you classify this sort of a data set. Let's say you're training a machine to identify what train this, you want to train it on this particular set of images, in the sense that you throw a coin, you toss a coin and you throw a die. It needs to identify whether it's heads or tails and the number showed by the die face up. How many classes would we have in such a case? 12, right? Because again, assuming that exactly one coin is present and exactly one die is present and one face is on top unambiguously, straight enough, right? So what you would do is, the stratification that you would do for when you collect data for this, you would just toy simulate the coin toss and the die throw a few times, capture the pictures, label them, and feed it into your model, right? But sometimes what happens is that, sorry, can I get rid of the tooltip over there somehow? Okay, yeah, all right. So this is the sort of contingency table you get, You see that even if all outcomes are equally likely, it's a uniform distribution across these outcomes, right? There are always cases where, some categories are very underrepresented. There's only one instance in a trial of 113 where the die showed 4 and the coin showed tails, right? And, again, there are only 2 instances each of the die being 6 and tails and 1 being 2, right? The die showing 1 happened in only exactly 2 images. So even with something like this where, by the way, the coin and the die are both fair, none of them is loaded, and you do 113 trials, this sort of thing still happens. And this becomes an object detection problem for you. So what would you do? Like, of course, the simplest thing to do is do data augmentation. Generating more data here is ridiculously cheap. I can just, ask a few people to click pictures and send them to me, and I could pre-train my model. But doing this actually in, realistic settings is not difficult. Secondly, the labeling is not going to be so trivial, right? But the idea is that even for something as simple as this, you could have an imbalance, right? And here's what I mean by the labels acquiring extra classes. When you're simply doing binary classification, your label for a given sample is exactly one element of a set of 2, right? And the label follows a Bernoulli distribution, right? But when it's a multi-class, then it's the same thing. It's a generalization of the Bernoulli. It has to be exactly one of a set of k elements. And the label follows a uniform or a binomial or a categorical, depending on whatever artifacts you see in your data particularly. But when it becomes multi-label, this time you're not sampling from a set of 2 or a set of k. You're sampling vectors from a large and complex distribution. So what this particular Y means is that the first image contains a cat, a dog, and a human. The second one contains a cat and a human. The third image contains none of the 3. And the fourth image contains only a dog. So you could have any one of the 3 classes. Any of the classes may be absent. And there could be images where nothing is present. So essentially what you're doing is you're sampling a vector of size 3, where the values could be any integers including 0, right? So you see that just by increasing the complexity or problems, the statistical distribution of the labels, it explodes in complexity, right? Stratifying and sampling Bernoulli is easy. It's trivial, in fact. So is uniform, binomial, categorical. But fitting a Dirichlet distribution itself is a non-trivial problem, right? And then again, ensuring that you actually sample well enough, that's another story entirely. Of course, if you fit it, it should follow. But fitting a Dirichlet distribution itself is something that's not intuitive. We are not used to thinking about sampling vectors from some function that generates vectors, right? And then when you come to actual object detection, it's like throwing another wrench in the works. This again explodes in complexity. You have the multi-labels plus on top of that, you have the bounding boxes, right? How do you stratify a Y which looks like this? There's no answer. I doubt if there is any clear or a good answer. We can only use heuristics, and some of those heuristics are essentially going to help us establish lower bounds on object detection problems. So you see that sampling labels is easy, but again, sampling for a multi-label problem itself is not easy. And then sampling for like, okay, am I looking at images with large laptops or small laptops or large chairs or small chairs? What is the median size? Do I know that the average size of the laptop in my training set is the same as the average size of the laptop in my testing set? And not only that, those sort of heuristics have to work for all types of classes, right? All types of objects for the stratification to actually work, right? And that's why the stratification here is key. We obviously know why we do it, because we don't want to ask our model out of syllabus questions. It has to have an idea. It has to, the data that is presented to it has to be representative, right? And the big problem, again, like I said, is that as the learning task evolves, the vector y acquires additional attributes, and therefore stratifying it becomes more and more difficult. And training labels, here's the hypothesis, here's the big idea of this talk, that training labels are interpreted as a joint probability distribution over a set of random variables. How well this holds out, we'll see in a few examples. For binary classifications, the labels are a Bernoulli random variable. That's obvious. For multi-class, they are a categorical one, or maybe a uniform one, or whatever the case may be. It could be binomial, it could be Poisson, whatever the case may be, right? What about multi-label problems? Dirichlet is one. There could be others. And what do you do with bounding boxes? What sort of random variables could you come up to describe the annotations in a typical object detection problem? Again, no answer. There are only heuristics. And we'll figure out how to mine these heuristics from the kind of mistakes that our model is making. But here's the big hypothesis which we are going to test through multiple experiments. That stratification means ensuring that the distribution of RVs, these RVs, the ones that you choose to define on your training data, in the training subset is close to the corresponding distribution in the testing subset. If that doesn't happen, there is imbalance, the model won't learn, there'll be overfitting and all of those typical problems. So you see that so far we have not talked about models at all. We are just talking about whatever inference we can mine from the data, because if you get this done and if you milk the data entirely to get the maximum learning possible out of this, then you have already sort of reached a lower bound. Other things like deeper models and data augmentation and gathering more data and all of those things could only improve the metrics that come on top of this. Right. So what I did was, I did 3 experiments on 3 different data sets which were varying in their complexity. So one object detection problem of them was very straightforward, very homogeneous. Other was very noisy, very difficult to track. And all of these were small data sets, because again, acquiring data for object detection problems is very, very, very difficult. And secondly, again, when typically you're doing POCs or something, you only have small data sets to work with, and you have to sort of, again, squeeze the last bit of performance out of that data set before you can get your hands on possibly a larger one, right? So 3 experiments, and for each experiment, what we are going to do is do 2 sets of training and testing. One is going to be a random 60-40 split. You see that it's deliberately kept very close to 50-50. It's not exactly 50-50 because I don't want to be unnecessarily harsh on the model. At the same time, I don't want it 80-20 because I want to squeeze the last bit of performance out of the model. What is the smallest stratified sample that you can give your data, give your model, so that it squeezes the last bit of performance out. So that's why the train test splits were kept at 60-40. One set of experiments was done with random splits of data, and the second set was done with stratified splits. Now, the stratification, again, we don't know, depends on the problem. Some strategy for a given example was concocted, and we tried to see how well it worked, right? And then we did 40 experiments each. So you see that on the table to the right, one cell is essentially the result of 40, 20 epochs, I guess, yeah. So for each experiment, what we have done is train the model for 20 epochs with a random split, throw away that model, I mean, not before recording the metrics, stratify the data using some informed random variable stratification, and then train it again, right? This time from scratch again, for 20 epochs, keeping all the other hyperparameters same, and then record the metrics again. Metrics in this case are standard map of IOU and dice coefficients and things like that, right? And then try to compare these 2 figures. So there are 40 random split experiments, each starting from scratch and going up to 20 epochs for a given fast RCNN implementation, which again preloads with ImageNet. the default PyTorch implementation. And then you stratify the data and do exactly the same thing. And then what we do is we try to compare these two groups of scores and try to see if one is higher and whether the difference is statistically significant, right? That we do by running a simple one-sided t-test, right? With the alternative hypothesis that one group is actually higher than the other. And then we'll see how often that test passes. Right? First example, very, very homogeneous data set, fairly simple in the sense that it's actually pretty much this that you see. In fact, you'll see that there is a cloth behind the chessboard and you can see some wrinkles at the top right corner. Even the wrinkles are constant. The background is perfectly constant across 202 images, fairly small data set. And these are not valid chess moves. It's just like, they put down a chessboard, randomly started putting pieces together and took pictures with a fixed camera. So the table is fixed and the camera is fixed, very homogeneous. Basically it boils down to, very easy object detection kind of stuff, right? And again, to reiterate, these are not valid chess moves. There is never going to be a situation where you have a single white or black queen on the chessboard. So again, it's not like people were playing and that's when they took these images. There are no humans there, nothing. It's exactly images that look like this, right? And the random split score, map of IOU, for the average of 40 runs here was 0.4 in this particular case. And here's the mistakes that the model was making. False negatives for single pieces. Whenever there is a single piece on the board, whether it is black or white, the model just fails to identify them. It's there, but the model says it's not there, right? It always confuses between bishops and queens. In fact, it probably confuses. The only consolation here is that it thinks that a black queen is a black bishop. It doesn't confuse between colors, thankfully. But that's anyway expected. You don't expect a fast RCNN to not understand color, right, for a similar looking piece. So the solution, I thought, was to simply stratify, since it had a lot of false negative for single pieces, simply stratify the number of pieces on the board. So you count how many pieces are there on the board and use that for stratification, right? The same distribution of number of pieces should be there in the training data, training subset and the testing subject, but that actually reduces the performance by 1%. The map of IU goes down to 0.39. But here is something interesting. You'll see that if you count the number of images, the number of pieces in this data set out of 202, almost half of them, 101, have exactly one piece on them. And the rest, follow that particular trajectory. So here we have sort of a unique opportunity to hack this data set. What I can do is simply segregate everything that has only one piece, 101 images that had exactly one piece, and treat that as a multi-class classification problem, because I just need to identify the piece now, right? So that stratification can be done as a multi-class stratification, the standard way we stratify any multi-class problem, and then the rest you just go blind with it, right? And when we did that, it turned out to give us a 6% statistically significant increase, right? There is no process here. These are just hacks. We looked at the data, and the trick here simply is to carefully note down the kind of mistakes the model is making in a very intuitive way, in a very human way. Try to figure out what the model is making and then see if there is a random variable somewhere which reflects those mistakes, which could sort of help us alleviate them, right? So yeah, that's basically stratify again. The remaining, we just club the single pieces image together, stratify by multi-class, right? The standard way we do it, just like we would do the iris data set, let's say. And then stratify the remaining by number of pieces. So this causes a 6% increase, and for 202 images, a 6% statistically significant increase is a lot, right? More data, we could do augmentation, we could do all sorts of heuristics that we usually do with object detection. That is only going to increase this as long as the stratification strategy is followed. And of course, the strategy holds only as well as you have this particular set of the data. When it changes, you have other problems to deal with. But this can be done repeatedly, and you see that this is cheap. This is practically free. This is just plain stats. So that's what I mean by no cost, right? None of this involves extra model training or any other expensive stuff, either in time or compute or data availability, right? The next experiment, this I think some of you must have seen. This is the standard PyTorch tutorial on object detection, the pen foot and pedestrian detection. So you see that the first column is the ground truth. Well, it's the image, it's the input, not the ground truth. The middle column is the ground truth. That's the true annotation mask. And what our model ends up predicting after a random split, usual 40 epochs and stuff, is in the third column. What would you say are the mistakes it's making? Sorry?
Focus on the non-related.
Correct, yeah. But maybe a little more specific. Sorry? It is, yes, it may be overtraining, but remember that the task is pedestrian detection. It's identifying humans. Even you see, pretty much the extra people who are being identified are people who are sitting, they're not walking around, right? And these false positives that it throws up are usually small. The pedestrian themselves are going to be fairly large relative to the size of the image, right? The other ones are small. So you see that in the first image there is somebody in the background, there are people sitting on the bicycles. In the second one, there is a big crowd. Of course, I would say that a few of those are pedestrians, but you know, there are people sitting on the lawn and benches and all who are not pedestrians. The whole idea is to learn pedestrians. So those are the mistakes. Too many false positives, and most of the false positives are people who are not pedestrians, and they are small. So how do you stratify this now? Like, these are the mistakes. What sort of strategy could be applied to this? Well, since there are too many false positives, the obvious thing to do is stratify by number of pedestrians in the image. That turns out to follow a Poisson distribution. Entirely coincidentally, it's clearly not a Poisson distribution because these are images from various places, not one place with a fixed camera or something like that. But if you do a chi-square goodness of fit test, it turns out that the number of people in a given image does follow more or less a Poisson distribution. The other interesting thing is that if you look at the size of the mask relative to the size of the image and convert that into a percentage, that follows a log normal distribution as well. So now I have these two random variables. One is and these are very closely related with the mistakes that it was making. It got the number of people wrong, it got the size of people wrong. So to account for the number part, we have a Poisson distribution. To account for the size or the relative size part, we have the log normal distribution. So now my image set, my data set becomes a distribution over the joint probability of these two variables. So every image is going to have some value on the Poisson distribution and it's going to have some value on the log normal distribution. And based on that, what I can do is simply tabulate the joint probability distribution of the two variables. It's actually not probability, it's just a table, but divide that by 170, which is the size of the data set, and you'll get the JPD, right? And now that basically what this table, what this JPD means is if you had, I just assume there's a pointer over here. But anyway, what this means is that there are exactly 4 people, or there are exactly 4 images such that the foreground of the masks occupies between 5 and 7%, and they have exactly 1 pedestrian in them. Similarly, there is exactly 1 image where the foreground occupies between 2 and 4% of the image, and there are 8 pedestrians in it. So given this sort of a tabulation, what I can do is I can split each cell 60-40. And 60% of each cell goes to the training, 40% of each cell goes to the testing. That is what stratification means in this case, right? Of course, literally this particular stratification doesn't work because you'll see that there are lots of cells which have exactly 1 image in them, right? So what you can do is always adjust the edges of the histogram so that you have more than 1 in each cell, right? Now, here's the interesting part. When we did that, additional 3% gain, but not statistically significant. But the variance of the stratified splits was much lower. So what we ended up with was something like this. The red histogram that you see, and again, the normal distribution is a little bit of a hoax there. It doesn't actually follow normal distribution. But just to sort of drive home my point, let's say that you had 2 models. one of them gave accuracies which were distributed according to the blue histogram, and the other gave accuracies which were distributed according to the red one. Which one would you pick? Why? See, there's a lot of room here, right? There's a lot of room here for you to do better under the blue model. But the problem is it has very little probability, right? Here, you may be conservative, but at least you're sure about the bounds are tight. It's like with the blue models, you are equally likely to do worse, right? So the tighter bounds, and this is, you see that the red mean is slightly 3% to the right of the blue mean. That's the 3% score that we got, but it's clearly not statistically significant. If you draw a sample here, there's no way to tell which distribution it comes from, right? So clearly the t-test fails here, but we would choose the red one because the model, the distribution is so flat that this is an indication of the model actually reaching its limits. It can do no better until we do something else. That is, introduce a different stratification strategy, or increase the number of epochs, or do data augmentation or something or the other, right? Lower bound again. Third most noisy data set. So we saw two experiments. One was very homogeneous. The other was, the problem was straightforward. The backgrounds were more or less there, but it was the problem itself was a little trickier. And secondly, the first one was, it wasn't exactly a semantic segmentation problem. The second one was, right? Everybody is, I'm sure, familiar with MS COCO, and what I've done for this experiment is slice out certain classes from MS COCO, basically most common kitchen objects like tables and apples and cups and saucers and things like that, right? So we have tables, we have apples. For some reason, on the top left, that whole red thing thinks is a table. Similarly for that one also. And again, we do the same thing. We train random, we split this data randomly 60-40, train and do 40 runs of trials. 0.3, that's the random split score. And these are the mistakes. Almost never recognizes apples. And any flat surface it thinks is a dining table. This is broadly was what's happening at the end of the random trials, right? And it fails to recognize cups when they are small, when they're in the background, right? So here, what could we think of? We need to take care of class membership here because there is cups, dining tables, and apples. There are actually 5 other things which it was doing fairly okay on. And then there is a, now I don't really know what to do about flat surfaces versus dining tables. Right? Because flat surface is not something that I can think of quantifying in a very obvious manner. Small cups is something I can do about. Size is there, size is quantifiable, and therefore I can create an RV out of it. But these are essentially the classes. There's apples, knives, carrots, bananas, broccolis, bowls, dining tables, and cups. And if you look at the mistakes, 2 of them belong to the most prevalent 2 classes, and the third one belongs to the rarest class. So that tells us something, right? That gives me some push towards how to stratify this. I can stratify by count, obviously, instead of doing it random, right? So 3 random variables over here. For the earlier we had 2, now we have 3, where one random variables, one RV is just number of apples, the second is number of cups, and the third is dining tables, right? How many cups do you have? How many apples do you have? How many dining tables do you have? When we do that, doesn't take size into account, so absolutely no improvement. It stays at 0.3, right? What else could we do? Now we need to start. Do I want to overly complicate this problem? Perhaps not, because 3 is too much. Like beyond that, I'll just start data augmentation, because now I don't want to do too much math, right? But if you just look at the densities of the sizes of different objects, you notice something very interesting. Dining tables are a bimodal distribution over here, which means there are large dining tables, there are small dining tables. Size, by the way, is measured as area of the bounding box divided by area of the image. So you see there is you can very comfortably split that between the 2 and have another random variable, because this is now a Bernoulli variable. I already have the 3. I add a 4th, easy enough to do, not too much, it's not too complicated. And when that is done, we simply have big and small tables. That's another RV to consider. And when we do that, stratified based on size of tables, we get a statistically significant improvement of 2%. Again, same size as the earlier data sets. The first one was 200 images, the second one was 170 images. This one was also exactly 200 out of the thousands that are there in MS COCO. But a 2% improvement in MS COCO with so little effort, I'd take it any day over trying to push my efforts into building deeper models or training more data and so on. Because this is practically free. This is something that I can do maybe in an hour or so. Doesn't take a lot of compute either, right? So there we are. We know that we can do better than random splits. So random doesn't mean fair. But it may, but it has to be verified, right? Find the mistakes that the model makes, and why I say write them down in English is that when you do that, that's when you sort of start getting hints of how you could model them for stratification further. See if the mistaken phenomenon are then represented or possible, if it is possible to represent them with a distribution. And then estimate the JPD of these random variables and use it. From that JPD, you sample your test data, you sample your training data. Whatever else you do, which includes the deep learning, which includes all of the other heuristics that we do in model training, that's only going to push things up. All of this deals with only the y part of it. When you do a model.fit of x comma y, all of this comes just from y. That's what I mean ultimately by no cost improvements. And the results here were statistically significant, or you could sort of reason about them in a way that actually makes sense, that it's not random anymore, right? So this is the problem, right? Large data sets are used to train these models, but when you're typically using them for a very specific fine-tuning problems, to begin with, if you get a few hundred images for a given problem, that's actually enough, and that's pretty much all that you're going to get. Annotating data is incredibly difficult, right? Getting more data is expensive. It's easy to overfit, and measuring performance is hard. Because when I say that something has a map of IU of 0.7, what does that really mean? It's not easy to reason about that. Whereas these things, they enable you to reason about the output of your model. I can say that I can detect big and small tables in the MS COCO dataset, right? So these are external heuristics that you could add to your process. But here's the problem, the very reason we do deep learning is that we shouldn't have to do this level of statistics on the data. We shouldn't have to think too much about, the data is a distribution over some arbitrarily defined, because if it is, then the model should pick it up, right? But yeah, that doesn't happen, unfortunately, because most deep learning models, in fact, in that case, when they are trained for a particular task, they really get good at that one task and they sort of neglect pretty much everything else, right? So overfitting them is very easy, so to speak, right? So yeah, when things get desperate, turn to the data, let the model rest for a while. There we are. Happy to take any questions. We have a good 10 minutes. Please. Right. It helps because if you were to do it randomly and then test your models, let's say you do a random split, you test your models, and then you simply make a note of the kind of mistakes it was doing. Like typically in a couple of years ago, I think there was this competition on Kaggle about detecting diseases on wheat crops, right? And the idea was simply to locate the diseased ear of the plant. And we, like a couple of friends and I, we got like really, really close to the top 10 on the leaderboard. But last moment it turned out that things that were leaves that were very thin in terms of a bounding box and those that were very flat. So it's like a tiny box either like this or like that. Those were the ones that we were getting wrong. Now how do I represent this, or how do I formalize this thought that that is what the model is getting wrong? Okay, then look at the width of or the area of the bounding box and see that okay, where the bounding box area is really, really too small, or the, let's say, not even area, aspect ratio in this case, where the aspect ratio is either too small or too large, the model gets it wrong. When I do random splits, there is no guarantee that bounding boxes with either too small or too large aspect ratios are being presented to the model at all. Because they themselves are rare, perhaps, who knows. So that's why stratification helps.
But there's a equally likely chance that
Yeah.
in the real world, you might have those rare cases coming up more often.
Precisely, precisely. All the more reason you should stratify.
Okay.
And of course, like the JPDs that we spoke about, you have to obviously keep updating them.
So the
Can't be-
assumption over here is that whatever stratification or distribution we have in the model is representative of the real world.
Yeah. Which is true for a very, very short time. Yeah. So for example, if I were to, this JPD for example, there's no reason that it will stay like this. If you were to, for example, like look at the top right box. If I were to take up, nobody's a pedestrian here, but let's say that if I were to take a picture of the front two rows in a very close-up scale, they'll probably occupy easily more than 50% of the pixels, and there are clearly 8 people here. Right? So it changes as your data changes, obviously.
Thank you so much for the presentation. It was very informative, first of all. And I have a couple of questions. First, what do you think about random errors? Do you think there are any? And second question, if you think there are, then how can we deal with it? Or how?
What do you mean by
can-
random errors?
Random, as in these errors that you listed down here are pretty straightforward, are visible by naked eyes. But there can be some errors which you cannot, make out pattern with your naked eyes. So,
Yeah.
what can you do with it?
Hard luck. I can't say it. Because that's what I meant by write the errors down in English. If a human understands qualitatively what's the error, then you have a chance. And I would even go so far as to say that random errors too can be sort of quantized. Let's take a very trivial example again for like this particular data set. Whether the coin appears to the right or the die appears to the right is randomly decided. This also is inferable from my labeling annotations, right? Assuming that this is a object detection problem. If it's a classification problem, I can't do anything about this.
One question.
Sure.
Regarding, for example, pedestrian problem. In that, you have considered size of the pedestrian with respect to the total pixel.
Yeah, yeah.
Possibilities where that okay, pedestrian can be back
Yes,
side and people who are sitting.
yes, yes.
can be front.
Absolutely, absolutely.
So it totally depends on the what problem we are solving.
True.
And that strategy will work or not.
Exactly. In this case, it worked simply because that was the dominant nature of the mistakes that my model was making. It was giving false positives which were small in size. So to do that trade-off, I didn't have a problem with large ones. Or in fact, I don't see if there is, the data by the way is also skewed. I don't think in this data set of 170 images, there is a single example of a small pedestrian who's like far away in the background. Pedestrians have always been shot from up close, and in fact, I think the reason is that the images have been also cropped accordingly before making the data set available. So yeah, that's quite possible. But this particular strategy was adopted only to correct for the current problem I had with the random split score for the current data set. Again, get 30 more images, your JPDs will change. Who knows? It will definitely change. Yes, please.
Yeah, I have two questions. One is what I see is it only applicable for small data sets, like you have taken 170 images, right? If you take, let's say, 1 million images, right?
Yeah.
Then it will be difficult to strategize, right?
Yeah, but the good news is that if you have a data set that large, you probably don't need to resort to all of this.
Can you repeat?
If you have a data set that is thousands or hundreds of thousands of images, you probably don't need to resort to all of this. There's enough information for the model to learn well.
No, but then also we have seen.
Then
right?
of course you can do this. Again, this doesn't cost anything.
Okay.
So,
And how?
there's always free insight essentially.
Okay, okay. And how would you strategize for? I think the assumption is right now on the sizes. Let's say.
Yeah,
on the,
yeah.
How would you strategize for the image quality? Let's say we have good data. Say
Yeah.
170 images.
Yeah.
A few pedestrians are of bad quality. The edges are not
Correct,
so clear.
correct,
Right?
yeah,
How
yeah.
would you strategize for that? Bro?
Is quality quantifiable?
Yes, let's say yeah.
Right. So then every image has a certain quantity. All of those, have some distribution. Sample that distribution. Quality can very well become a random variable for you to sample by.
Okay, so first I just want to understand like the whole process. Like you'll first try to get the edges and then.
So figure out how to estimate quality first, right?
Okay.
I would probably think of things like blur, how blurred the image is, how sharp it is, how dull it is, how bright it is, and so on. If it looks like a particularly bad image, then I give it a low score or a high score and calibrate that scale and figure it out.
Okay, thank you.
Yes, please.
I think very nice presentation.
Thank you. Thank you.
One of the things is that since the data is really sometimes, like you were saying, can cause the error because the error analysis goes back. So if it turns out that the quality of data itself is causing that, so one of the strategies to strike it at the root and say that these kind of images should not be taken or should not be.
Precisely. Yes. Correct.
Controlling the quality of the data is preemptive, and one can probably do that.
Wonderful. Yes. In fact, an extension of that here would be clip your PDFs in the right places. They shouldn't have outliers or shouldn't appear to be unmanageable.
The data generation process itself has to be targeted
Precisely.
to ensure that quality is good, and then everything else.
Exactly. Agreed. All right. Thanks a lot. I'll be around and feel free to reach out to me, find me.